Okay, so here's a mechanism for the Aldol reaction. So this is chapter 21, Aldol addition, and then over here, the condensation. Okay, so if you run this reaction and you don't heat it up, you'll get this product in brackets. If you heat it up, you'll get the alpha beta unsaturated aldehyde down at the end. So go ahead and hit pause and come up with a mechanism for how acid aldehyde under aqueous basic conditions can turn into that product, which is actually formally called Aldol. Okay, slide back off the thing here. Okay, now that you're back, so we've got base. Right, so sodium hydroxide is basic, so you can't have strong acids here. Right, we can't protonate anything. We can't have oxygens with 3 bonds. And so let's break this down as we're looking at it. Our product has 1, 2, 3, 4 carbons. And you might actually look at this and think, oh crap, my starting material only has 2 carbons. Yeah, well, 2 times 2 is 4. And remember, the thing that's over here, you have more than one of it. Okay? So acid aldehyde is not a single molecule. This is something I find beginning students get hung up on, that you just want there to be one of these. Again, I think I said this in another video. Let's say we use 1,000th of a mole, so 1 millimole, okay? So that is, a mole is 6 times 10 to the 23. So if we have a millimole, we have like 6 times 10 to the 20th molecules. So you certainly have 2 to put together. Okay, and so if we can use more than one of these, we have 4 carbons in the product. 1, 2, 3, 4. There's 2 here. Probably 2 of those are going to react together. Okay, so the first step, we have to make acid aldehyde nucleophilic or electrophilic if we're going to bring them together. Under basic conditions, it's going to be easier to make acid aldehyde nucleophilic. If we had acid, we could protonate the aldehyde and make it electrophilic. So hydroxide, OH bonded to a sodium is going to be ionic. That base will take one of the protons off the alpha carbon, and we get an enolate. In this case, a sodium enolate, plus water. Okay, it's aqueous base, so there's already a lot of water around. There's our enolate. We can draw an HN, we can draw them all in here. Okay, this is actually how the enolate looks. Carbon-carbon double bond with a CO single bond to the O minus. All 4 of these atoms, the 3 hydrogens and the oxygen, well, actually all 6 of the atoms are coplanar because the 2 carbons look like sp2 hybridized carbons. So it's an enolate. Strong base. Good nucleophile. And also I've drawn sort of a 50-50 arrow here for pKa of water is what, 15.7. pKa of this proton is about 16. So this really is pretty much a 50-50 equilibrium. Okay. But it's 50-50. So you're not making this enolate. I'm going to get rid of the sodium counter ion too. You're not making that enolate and then having it just sit there. So if you want it to react, it's got to react with whatever's in solution with it. Well, what's in solution with it? Hydroxide, you're not going to pull more protons off here. Water, if the enolate grabs a proton from water, you just go back up to the starting material. That's just a back reaction. That's it, except for acid aldehyde. So we've got some acid aldehyde still in solution that's neutral. Remember, it's 50-50, so you've got some enolate, you've got some of that. Remember the resonance structure here for the enolate has significant negative charge on the carbon. So it looks like the green enolate, it's going to react like this black enolate. we need to make a bond between an alpha carbon and a carbonyl. So this negative charge just straight up attacks the carbonyl. So let's number these according to the system I did up above. So aldehyde is 1, 2, 3, 4. That is going to give us, and again, this is a reversible process. Carbonyl, compound, or atom 2, bonded to another, what used to be a carbonyl carbon, but now the pi electrons have been pushed up onto the oxygen. Again, we're going to get a base. We're not going to protonate this aldehyde first. We're just going to get straight up attack to get a base. 1, 2, 3, 4. And now to get there, we just need to react with water. So the O minus can take a proton from water. We get aldol. This is actually called aldol because it's got an aldehyde and an alcohol. And we regenerate hydroxide. So this is catalytic in hydroxide. Up until the addition product, this is the addition product. Catalytic in base. Okay, now I've also said that, and that's it. That's the whole mechanism for the aldol addition. All the aldol reactions we're going to see, I've got another one out there, another video out there where we use a stronger base, but all the aldols are enolate type of reactions. We're going to have a base, take an alpha proton to make an enolate. That enolate is going to attack a carbonyl compound of some sort. Okay, let's come down here then and look at the condensation. Here we are, we've made this compound. This thing's floating around in base. And we're going to get an alkene. So this looks like an elimination reaction. Hopefully you look at this and think, wow, that you're losing an OH. So this is elimination. But it doesn't look like you should remember from Orgo 1 that hydroxide is not a leaving group in either E1 or E2. So you might think we got to protonate this OH to get rid of it. Sure, but you're in base. You can't protonate the OH because you don't have any acid. Well, maybe make it a tosylate. Well, again, you don't have any tosylate here. Make it a chloride. You don't have any thionyl chloride. You've got to only go from here. So just basic review. For these mechanism problems, we show you everything you need. Okay, there's nothing else in there except what we give you. And so here's what happens. We still have alpha carbons. The hydroxide takes the alpha carbon. Get the enolate. Another thing, never take this one. All right, the aldehyde carbons, the aldehyde hydrogens, that's not acidic. So your base is never going to take the aldehyde proton. Okay, so we make an enolate. I really have a feeling my red is not visible. So you make an enolate. Again, this is kind of 50-50. pKa there now with the added stuff is probably 17 or 18. So it favors the start a little bit, but it's there. You could, what am I trying to say? You've got a significant amount of this. And now remember, the enolate's a strong base, it's high energy. So now this negative charge can kick out hydroxide. And there you go, you get to your product. Why can we lose hydroxide here and we can't lose it in an SN1 or SN2? And the answer comes down to how reactive your starting materials are. All right? So in an SN2 reaction, you've got a nucleophile. Any nucleophile that's strong enough to kick out an OH is going to be a good enough base to pull that proton. Okay, so the difference here is we can make an enolate And now it's one molecule that's very high in energy, and it can relax by kicking out hydroxide, which is actually a weaker base than the enolate. Okay? You might wonder, well, why doesn't hydroxide take this H occasionally? It does. Sorry about my voice. Right. Hydroxide can come and take that H, fine, but then nothing happens. There's nowhere to go. So the O minus just takes the proton back for more. At higher temperature, so now again, we get to temperature. So again, this is, elimination is favored at high temperature, right? Elimination is favored at higher T. Okay, and so if you heat this reaction up, you get what's called a condensation product, because you actually lose water in here. You make an equivalent of water for all this. Right here where hydroxide grabs that proton, you make water. And so it's condensation. If you do this reaction in an organic solvent with organic molecules, you'll actually see water build up on the sides of the flask, and it looks like water is condensed on the flask. How it got to be called a condensation 150 years ago. All right, we call this a simple aldol reaction because it's one single carbonyl compound reacting with itself. Right, so the simple aldol is a weak base deprotonating an aldehyde or a ketone, and then that aldehyde, the enolate of that aldehyde or a ketone reacting with a second equivalent of itself, and then either giving the aldol product or the condensation product. The point is, it's fairly limited in synthetic use because you have to be trying to make a molecule that is a dimer of the simple one. The directed aldol, where we use a stronger base, LDA, and there's another one of these videos online for that. That's a much more synthetically useful reaction because you can make the enolate of whatever it is you're using. You know, you can make one enolate, make it completely, and then add in a second carbonyl compound to be the electrophile. So you get more molecular complexity. But this is how it was discovered, and if you need that molecule, it's still a really simple reaction to do. And it's good to keep in mind if you're ever working with aldehydes or ketones that you need to keep them away from decent bases and acids. Okay.